Hello. I would like to spend a little time just talking about transformers. We're not going to do a whole lot of detail with transformers, but it is a useful concept to do at this point. And by transformers, I don't mean this kind of transformer, but this kind of transformer. The kind of transformer that you can see outside of your house, in your neighborhood. They come in all different sizes, and the purpose of a transformer is this is a simple example of a transformer. All a transformer is two coils of wire that are in the vicinity of each other. And in this particular example, you can see that out here there's this coil, and here there's this coil, and the two coils are tapped into with these connections here. And there's just two coils of wire that are in the vicinity of each other. That's what's in here. There's a coil of wire and a second coil of wire inside of this, and these can be seen outside on your telephone poles. There are also larger transformers. The green boxes around campus, the very large green boxes outside of buildings, are transformers. And the purpose of a transformer is to step a voltage up or down, a potential difference up or down, meaning that, let's say the power company sends 100,000 volts over their high voltage power lines. They send very large voltages for reasons of, if you send a large voltage, then you can send a smaller current for the same amount of power, since P is equal to IV. And current is the thing that heats up the wires, so you want to get the current as small as possible. So a power company might send over high voltage lines 100,000 volts. I'm not entirely sure if that's the correct number, but and when it gets to your house, what does your house need? Your house needs 120 volts. So you need to step the voltage down from, let's just say, 100,000 volts to 120 volts. And how do you do that? We've already seen in lab that you have voltage dividers that allow you to take a larger voltage and make it a smaller voltage. But with a voltage divider, you lose a lot of energy through the voltage dividing process. The resistors use up a lot of energy. So the beauty of transformers is that it's not really a lossless, but it's theoretically a lossless way of changing a potential of stepping up or down a potential, changing a potential from 100,000 volts to 120 volts, from 120 volts to 5 volts, or from 5 volts to 120 volts, and from 120 volts back to 100,000 volts. You can go up or down, and it's theoretically lossless. It's not actually lossless, but certainly you lose a lot less energy than with a voltage divider. The disadvantages of transformers is they only work with AC power. They only work with changing voltages, because transformers work using Faraday's law. Faraday's law says you induce a voltage when you change a magnetic field. So if you have a changing magnetic field, you can induce a voltage. If you have a changing voltage, you've got a changing magnetic field, and you can induce a voltage. So transformers only work with AC power, with changing currents. It doesn't work with constant or DC power. So if you've got DC power, you've got to use voltage dividers to change your voltage. But if you've got AC power, if you've got changing power, right? With AC power, it just means that the current and the voltage are continually changing up and down and up and down. Then you can use a transformer. So how does a transformer work? Well, a transformer, just keep an eye on the top here. The transformer works by having two coils of wire in the vicinity of each other, and they're not attached, right? So that's the whole idea here, is that they're not attached. There's an insulator, the white thing, that is in between these two, right? So there's your insulator. The coils are not attached. So the easiest way is to put the coil one inside of the other. Or you may put the coils one next to the other, like I do here, and you can help to increase the ability of the transformer to do its job by putting some kind of ferromagnetic material in the centers of the transformers, right? Put a piece of iron, and what that does is it enhances the magnetic field from one coil, and that impacts the other coil. So what's the point of a transformer? The point of a transformer is that you put a potential difference, an AC power, into one transformer, and so now you've got a so let's say that this is your high voltage power supply, 100,000 volts, and it's AC power, and you're putting that AC power into one coil. Well, that coil is going to have a magnetic field, right, inside of it, which influences the other coil. And that magnetic field is going to be a changing field because it's a AC power supply. And so that changing field will induce a current in this other coil. So it's going to induce an EMF or a current in the other coil. And the induced EMF, let's just call this E2 and this E1, right? E1 is whatever you put in, E2 is what you get out. And this can be attached to your power supply of your house or whatever, or whatever you want to transform the voltage to. Doesn't have to be a closed loop right here. It can be a closed through whatever device you're powering. So the induced EMF is going to be different than the original EMF. E2 is different than E1 if the number of coils, N1, is different than N2. And let me show you why. So I'm not really going to be able to explain why because we didn't spend enough time with inductors talking about how inductors work. But let me just justify it. That coil number 1 has N1 turn loops in it, and it's got an EMF that we're putting into it, a voltage that we're putting into it. I'm sorry. I guess I should be a little bit careful. It's actually got a voltage of delta V that we're putting into it. And when we put that voltage into it, it's got a self-induced or self-inductance. It's got a self-induced EMF, which is equal to N1 times the number of coils in the first solenoid times the rate of change of flux in that loop, which is dependent on the potential difference that we put in. It is also going to, like we said, induce a EMF that's here, induce an EMF in coil 2. So it's the induced EMF in coil 2 is induced, right? There's N2 coils in coil 2, but it's induced due to the rate of change of magnetic field or rate of change of flux coming from coil 1. Again, I'm not really justifying these equations, but we're just gonna take it and go with it because these are correct. And we don't have time to justify them all. Okay, so we've got a self-inductance. So this is basically the potential difference in coil 1, and then an induced EMF in coil 2 due to coil 1. And so now you combine those two equations and you get what's called the transformer equation. You combine those two equations, right? There's a common d phi dt in there. Again, because this is a self-inductance in coil 1, and this is what's induced in coil 2 due to coil 1. So this is still the flux due to coil 1 that's in coil 2. Okay, so those two combine to give really this last equation, which is called the transformer equation. The transformer equation says that the ratio of the voltages in the two coils is equal to the ratio of the number of coils in the two coils. So if you want to step a voltage down, you need to step down the number of coils in the solenoid. So if you want to step a voltage down by a factor of, let's see, 100,000 to 120, that's about a factor of 1,000, then you would have a factor of 1,000 fewer loops in solenoid 2 than solenoid 1. So solenoid 1 may have, 1,000 loops, and solenoid 2 may have 1 loop. There's a factor of 1,000, so that steps it down by a factor of 1,000. Or for reasons which we cannot go into here, maybe solenoid 1 has 10,000 loops and solenoid 2 has 10 loops. There are other reasons for choosing the number of loops. So the transformer equation just tells you that the ratio of the two voltages is equal to the ratio of the two coils. Super simple. So here's the idea, right? You've got, we do this all the time. You've got 120 volts in your house voltage, and your laptop only needs 5 volts. it actually, even though your laptop may be rated at the different voltages, typically it really only needs 5 volts. But let's say it needs 5 volts or 9 volts or 12 volts. You can look at the bottom of your laptop and or your phone or whatever and just see that it doesn't require 120 volts. And actually, if you put 120 volts into your laptop, you're going to destroy your laptop. So you need a transformer, right? So you get this thing. This is a transformer. This little plug thing that you plug into your laptop is a transformer. And that transformer takes the 120 volts and transforms it to, let's say it's 12 volts, right? So let's say your wall plug is 120 volts, your laptops need 12 volts. So how do you make a transformer to do this? Well, right, you would take your 120 volts and you would put it into some coil, and you would have a second coil that is fewer because you're going to step it down, and you know that E1 over E2, or E in, let's call this E in over E out, right? E in is your wall plug, E out is what you're going to your computer with, must equal to N2 over N1. So N2 is what's connected. All right, we can call that in and out. There you go. So therefore, 120 volts in, we want 12 volts out, so that equals 10. So we've got to have N1, you got to have 2 coils where N1 has 10 fewer turns than N2. And so that's what's in that plug thing that you plug into your computer. It's basically 2 coils connected by some probably with a ferromagnetic material, some kind of magnetic material, just in there, just connecting giving a better magnetic connection between the 2 coils. And that's what a transformer is.
I stayed up all night, wondering where the sun went. Then it dawned on me.